a great question. Dude, he was sick yesterday.
Okay, some good news. I started my little error board and it works. So which means if you do the same similar projects, it will work as well for you guys. What's that?
Just for clarification, so if we're doing track 2, this upcoming lab, we're just doing task 14 and then our project, correct?
Yes.
Not task 15.
No, not at all. Yeah. So someone has a question about the USB ports and the footprint. It works, no problem on that. And USB communication programming works. I loaded the lab 6 or 7, I forgot. So I can reset it. I can message it, type a hello there, and send and receive, no problem. So the only thing difference is the IR emitter here is upright. It's shooting up. Remember the one we had on the paperboard is shooting to the side, right? You probably didn't remember, but it's okay because the IR is going to everywhere. Right? It's bouncing back and forth, but eventually it's going to arrive this decoder and do the job. So that's good news. So if you follow my tutorial and we solder it correctly, it should work. Okay, there's a good chance that it's going to work, especially for the IR part. Okay. And if you look at the schedule, this will be the last in-person lecture I'm going to give for the semester. So after this, we'll have no other in-class lectures anymore.
After today?
After today, if you look at the schedule, that would be so sad. Take a look. So today we'll cover, because there are so many people working on track 1. All right. So I'll cover the remaining part of lab 14 and lab 15 as well. So let you guys know the expectations for that and which part is being used for the task 4 of track 1, which one is being used as a regular lab. So I'll make super clear on that because this is a very big puzzle to solve. I was trying to accommodate every single one's interest and bandwidth, so it's making super complicated. If you see problems, let me know. Okay, it's a very big puzzle. It's like lab 15, lab 14, like drop a lab.
Is lab 14 the only one you have to do if you're on track 2?
Wait.
Okay.
Okay. So remember before when we were doing the regular labs, we work on a lab, we demo it the week after, okay? And then during that week we do a new lab and then we demo it the week after. So totally, if you want to finish everything about 2 labs, it takes 3 weeks. Okay? So now we have only 2 weeks left. So how do we do that? First, I reduced a lot of workload for lab 14 and 15, so make it doable within 2 weeks. So we do the lab on Thursday this week. You can see there were like 10 questions for lab 14 and 15, and I reduced it to only 2. Only 2 questions, only the essential ones that you need to know to perform on your project. That's it, no other things. So for lab 14, for the in-lab, let me show you. Because everyone is doing that, right? Need this. In-lab 14, take a look. Only 2 questions. So only 2 things you need to know. What are the 2 pins being used for I2C? This could be a very critical knowledge that you need to know. Remember I told you guys, for SPI, what are the pins for SPI communication? It's being treated as a common sense for electrical engineers. Just have to know it for the interview purposes or for everyday engineering practice. So what are the SPI ports? SCK, DIDO, right? Clock is called SCK, keep in mind. If you see SCK, it definitely has to be SPI. Is that clear? SCK has to be SPI, all right? And you got DIDO for the SPI modules and power and ground. Okay, that's it. For I2C, you have one last pin. So you only have clock, which is SCL. Remember, if it's SCL, it cannot be SPI. It has to be I2C, right? So I2C is running at a lower speed, but it's reducing the number of pins to save the pin resource on the chip. So ICL, if you see SCL, it has to be I2C. And SDA is the data, just one data input and output, managing two directions. Is that clear? So that's why for I2C, we are only seeing ICL and SDA over here, because one clock, one data pin, both input and output. Okay, it's bi-directional communication. And then VCC and ground, that's it. It's probably there will be a table or a chip diagram on the final exam to ask you what's communication protocol being used for this chip, right? Things like that. Or I can tell you if it's I2C, what's the name of the data pin, what's the name of the clock pin, okay? Things like that. And then this is for instruction for soldering to let you identify the parts. Over here is labeled as all the different letters. So Carlson did that for you guys. It's really nice. So you can tell K is a connector and header pins and all these kind of buttons being used for the soldering. Okay, so you need to identify the parts and then find out the corresponding lettering in this picture and fill it into the table. So that's everything you need to do for the in-lab. Okay, if you split tasks in between you and your lab partner, you can get it done 20 minutes or so, hopefully. But you have 3 hours. So that's why I think it's very possible you'll get both for track 1, because we have so many people on track 1. You can get track 1's lab 14 and 15 completed by Friday this week. But the due dates for the demo for lab 15 is next Friday. But I think there's a good chance you can get it done by Friday this week. Okay, so now let's take a look at the, well, it's not opening. All right, to explain this assignments really quick, but before we go there, let's look at the schedule one more time. So what are you expecting this Friday? So Friday's the last lecture for this week, right? We don't have a lecture on Friday. So the goal is to let you guys, because I know there will be a lot of soldering problems. Most of you are beginners. So start soldering on Thursday. If you see the EDC lab getting crowded, you probably won't be able to have a spot for the soldering iron. So that's why we leave Friday for you guys to get it done. The reason for that is a lot of people on track 1. So you want to finish lab 14 and 15 as soon as possible. So you got a functioning board. You can focus on the project for track 1. It's taking 20%. So you can focus on that next week instead of waiting and doing lab 15 next week. Let's try to not work on lab 15 next week for track 1. So get it done this week. Friday, we'll give you the time during the lecture if you want to solder the boards. If you didn't finish it on Thursday, solder it on Friday, or troubleshoot it on Friday, and I will be there in my office area to help you out. If you have questions, let me know. I'll help you out to get the board functioning by the end of Friday. So you can use the weekends and next week to work on the project. So what are the projects? What are the projects? It could be 4 of them, okay, 1 of the 4, or it could be a self-defined project like your experiment, doesn't matter. I mean, he required students to do both, but you just need to do 1, okay? Just pick up 1 and make a meaningful project. I don't have time to approve proposals anymore, so you just, during the presentation, you just have to make it meaningful. You cannot just tell me it's a vibration, and it vibrates for 5 times. It's not meaningful, right? It could be like a door counter, like step counter, and just demo to me, it works. What's that?
So the board that we're soldering on tomorrow, that's got the accelerometer and everything?
Yes, yeah. So use it for the project.
Okay.
Yeah, and
It doesn't detect like tilts and stuff?
yeah,
Or
yeah,
just
yeah,
the-
both. It's just acceleration and angle. You can use the acceleration to calculate angles. I'll show you how to do that
So it does
in a bit.
periscope as well?
Yes, yes,
Okay.
yeah. So it just need a little bit of data processing, signal processing. After you receive the data into PuTTY or the IC card, you can split it out, and then do a post-processing. So there's nothing to program with the PIC. If you are willing to program it and integrate that I2C's reading function, the variables, do something, which is someone is working on it for track 2, a burning alert, right? Tune it, get the angle to the I2C read, to the variable, and make the speaker to peep. That's track 2 project. But if you are willing to do that, you can still do it. Highly recommended. But you are not interested, for example, you want to focus on power electronics in the future, not microelectronics, but power or E&M simulations or other path, right? Other concentrations. You can just do whatever the minimum requirement, which is just finish one of them or something similar. Okay, so we'll run. So for task 5, eventually will be a in-person demonstration. I was thinking about doing everything in class. It could be something against the FERPA because in the meantime I'll negotiate with you for the grading. So in-person demo I directly issue the grades, right? It's better to do it in my office, and I'll probably select some of the presentations and do it in class. But we'll try to figure out later. Okay? Because some of you guys probably it's better to share, right? If you have done some really creative work, so we can share in the class as well at the same time. I was planning on a symposium, have posters in the classroom, and have the TAs come to visit every single poster and issue the grades, but it's not realistic. I mean, it's taking too much time to do it. So unfortunately, we won't be able to do that. But do you enjoy that kind of process? Like symposium, have refreshments and lunch, pizza, and Anyway, okay. All right. Come back here. Take a look. So lab 14 is a regular lab. It's just a regular lab. Nothing different, nothing special. Lab 14. Everyone should do it. And if you don't want to do it, but still want to get a grade, let the TA know. It's going to be one of the labs you want to drop, right? So you can request a full credit. But this Thursday, you still have to show up to work on the project in order to let the TA issue you that full credits at the end of the lab. Lab 15 will not be posted in this section because lab 15 is not a lab anymore. If I put it here, it's going to take that percentage and weight here. So I have to place it as task 4 here. So see, I have 2 tracks. Couldn't read it, but it's okay. You'll see this later. So for the in lab 15 and lab 15 demos, for track 1, okay, this is 200 points. Keep in mind, 200 points for track 1. You finish the in-lab questions and lab demos, just very fundamental demos. It's not a project demos, okay? Just lab 15 demos, very fundamental, like case A, case B, case O, things like that, right? So totally 7 problems, including 2 in-lab problems and 5 demo problems, taking a certain number of points, okay? Try to finish everything before the deadline, okay? So the TAs will be able to grade it for you. You're getting 200 points for task 4, which is taking 50% of the project. For track 1, does that make sense? A lot of students are in track 1. Does that make sense? Any questions on this? Is lab 15, in-lab and lab demos part of the project? It is. It's task 4 for the project, but not the project demo for task 5. Okay? So one of the 4 listed projects for lab 15 will serve as task 5 credits. Okay? In-lab and lab 15 fundamental demos due next Thursday or Friday. But highly recommend you get it done by this Friday because they're very doable. Again, doesn't matter. So in lab 15 and lab 15 fundamental demos are in task 4. Okay? And for one of the four listed or self-defined accelerometer projects for track 1 will be served as task 5. Okay? So track 2, task 4, due next Friday. It's going to be an in-person demo for the PIC board demo for the project. Okay? Nothing to be submitted. But PIC board demo. No PCB yet. If you got PCB done, you want to demo both at the same time, perfect. Okay? That's even better. So we can get 2 done at the same time. So PCB demo, entire system demo, and slides presentations will be task 5 for track 2. Task 4, only PIC demos. Okay? Plugging the sensors, jumping wires, and everything. But make sure if it works the night before, right? You want to record a video because jumping wires are not reliable. you carried it to my office. Eventually, there are some disconnections, and you want to tell me it worked last night. How could I know, right? Record a video the night before, so I know it worked. Okay. Any other questions for the rest of the semester? It's so complicated. Oh my goodness. I taught 300 students this semester. So in the past 8 years of my career, I've taught probably less than 300. So this semester I got 300 students for 3 classes: PCB, embedded, and circuit 1. Okay. Any other questions anywhere else? This is my last lecture, okay? So I'm gonna cover that. I'll let you guys turn it in. Then we are done for the in-class exercise. There are 5. So I had 3 of them not graded yet. I'll grade them and you should use that points, bonus points. And so Friday, remember Thursday, Friday, the reason I'm not giving lecture on Friday this week is what? Let you guys finish up all these lab 14, 15 stuff. So are ready to work on the project for track 1 next week. Okay? Okay, so next week, no lecture at all. Give you the time to work on the project. Hopefully you can enjoy it. I know you have super heavy workload. Try to work on the project 20%, okay? You guys like, no, I'm gonna work on devices exam on that day. I know you guys are bumped. I mean, it's so different here. Everyone just want to do the minimum work because the workload is so heavy. For us, the students are just want to do the maximum because they got a time to work on it. They're asking for more to add more, but here it's like you guys just want to do the minimum as long as I can pass it. Done. What's that?
Sorry, this isn't super related. I was just curious if after all these in-class exercises were graded, if you'd have the solutions on Canvas so we could study them later.
You mean the final? Oh, the solutions? Yes. So the solution for the 5 in-class exercise, and I'll give you another extra probably, let's say 50 to 100, maybe 50 or something, problems and list it in there and give the solutions, and eventually I will just pick up like 20 from them. So you don't have to guess. So what kind of problem Dr. will put on the final exam is all there, okay, in the 50 problems on the list. So just study it. I'll just change the numbers. Very doable and reasonable. So I also will occasionally accept extensions for projects. Because taking 20%. If you think you want to take the time to work more on it, probably we can see if we can, let you demonstrate it on Tuesday or Wednesday of that week, about like 3 weeks from now. So I have a lot of time instead of rushing here, okay, or here. The goal is to let you really think through the whole process and get the project done, Even though learning the fundamentals are important, but I think the most important part through my engineering career is to learn how to divide a big problem into smaller ones. So I was talking with Cynthia, who is working on the burning alert this morning. So it was scary for the very big scope of the project. How do we, make the I2C to work and get the data in and save in the variable and use that data to set a threshold and then do the beeps, right? Sounds like really scary, intimidating. But I told her, for example, let's just forget about the I2C at all. So what about you just use the push button, like push it, give a signal, like to simulate that there's an angle change of the burner knob, and then just beep a speaker. We have done this so many times for like 5 or 4, right? Just divide the big problem into smaller ones, do the push button and beep it once, because we're expecting the customer will probably want to hear another beep if the angle is still unchanged. So beep for 5 seconds and wait for another 10 seconds and beep for another 10 seconds, right? So do that first. And then change the button to a variable like constant, for example. So like use the push button to keep incrementing numbers to simulate the real world that the angle is changing, right? So you still don't touch the I2C. But eventually you got another team member on the team to not doing anything over here, but just working on I2C. Get a data read from the I2C and save the value and send it to the party, to party. to display the angle change. So eventually you merge these two problems into one, or program into one, to make it work, right? So I think how to tackle these big scope problems will be the most beneficial thing you learn from this class through the project, I think, at least. All right, so now let's, if you don't have other questions, we'll start working on that remaining problem, then we'll wrap up today, okay? No questions on the project and anything else? Okay. So we were where? 6? How fine focusing control is achieved? We covered the code last time. You just describe it. So the fractional parts are getting accumulated to the phase accumulator and eventually get effect shown to the integer, right? Or manifest to the integer number. But you understand what happened, right? No? Puzzle? Okay. Where's the code? Here. Code. Remember this one we did last time? And remember there was a sprite sheet I showed you guys last time? Right? So these are the index being used to access sine wave points, right? But however, the step's too big. There are only like 16 points. How could you have like 10 point step every time? It's not working. So, but we can still use this integers, and we divide it by a certain number, so we don't have to mess with floating point or fractional numbers in C. Okay, we divide it and only extracting the integers. So see how that works. If you divide by 4, it's still not good because you can see the step is too big, like 2, 5, 7, 10. You only have 16 points. Keep in mind. What's that?
In like 2 sentences, this means like, are you doing like a big for loop and try and add up a bunch of numbers? Like,
No.
I'm just trying to understand what the essence of this is.
Yeah, that's why I'm explaining, right?
Pretty details, but like the 15,000 foot view, what is this?
I can't. I cannot just give you like 2 sentences for the key, right? I will after I explain this, but I can't now. Okay? I cannot just directly give you the key. That's the point I'm here. I'm not. All right. So if you divide by 16, I can see the integers are changing from 0 to 1 and 2, 3. So it's not changing like taking big steps. All right? So in that case, you can access to every single point, but also changing the frequency of it. So, but you can see even though the fractional number is not being used at all, but eventually it's adding up, and eventually manifest to the integers, but accumulate it and change the integer part of it. Does that make sense?
Not really.
So, for example, 0.5, right? But if you have two 0.5s, you accumulate it, you got a 1 for the integer.
So this is just a sum, a big sum?
Yeah, it's accumulating the fractional numbers, so it's adding up because these are accumulated, so it's adding up to each other eventually.
It's a moving average.
Is that moving average?
Or is it a sum?
No, it's just a sum. So it's like the fractional numbers accumulating, but eventually change the integer. Okay.
Just
What's
to
that?
clarify, this is fine frequency control using phase accumulator?
Yes.
Okay.
So fractional parts again.
So the fractional numbers are, let's see here. That's a final effect, right? These numbers, only the integers of these numbers are used. does that make sense? Are used as the index to access the sine wave array. Okay, let's take baby steps. Take baby steps. So these are the final values are being used as an index for the sine wave. Okay, and because they are integer variables, so we're only extracting the integer part of it. Okay. If you look at here, look at the code, the phase, even though you're adding 10 to it, okay, for the phase accumulator on the very left side of this guy, but eventually you divide by 16 to make that happen. You divide by 16 to reduce the overall number of it, the size of it, but eventually extract that number as an integer for the index of the sine wave. And that's why, because we cannot just, like I told you guys last time, we cannot create 3 columns in our brain. That's why I just showed you these numbers. So these are the integer part of these numbers are being used as the index. And you can tell the difference. If you just directly use the 10, 20, 15, like the ones not being shifted, these are like taking big steps. And if you divide by 4, it's still big steps. But if you just use it, if you divide by 16, and now you can tell it's not that big anymore. Okay? So by accessing this index into the sine wave, you are able to recover the entire sine wave. Okay? So what else do you think we should demonstrate here? Will make more sense here. Think about it. Helping you and everyone else understand what's really happening. So now we are taking what as a phase increment?
Just the integer part?
10. Well, I mean originally 10, right? Okay. You want to see what if we change it to something else? Yeah, curious? Can we do that? Let me see. So it's gonna be 0 here. So I'm gonna add 2. Okay. See if that works. All right, good. Okay. Then I'm gonna do by 16. Okay, let's just look at 16. Divide by 16. So this is serving this index, okay? All right? Why we want to divide by 16?
Because we're right shifting it by 4 bits.
Yes. So we can have smaller steps, right? It's not like taking 10 steps every time. I only have 16 points. I only have 16 points in the sine wave. So we want to take smaller steps. Let's just sample some of them. What's the difference?
It spends a lot more time on the same index, so it'll spend like, what is that?
So which one has a higher frequency though?
Oh, the first one.
Yeah, definitely. Okay. Does that make sense? If you look at numbers, if we take a phase increment of 10, you are generating a higher frequency. This is the lower frequency. Why is the lower frequency of the sine wave? Why is the lower frequency? Can you tell? It's always sampling the point 0, right? So what's really happening? It's not changing, but your time is changing, but the point is still the same, right? If it's not changing, it's a low frequency or high frequency?
Low frequency.
Yeah. Make sense? Okay? Still want a 2 sentence to cover the key? I think the Excel sheet explained it, right? Make sense? Okay. Try to organize your own language. Your English is way better than mine. My Chinese is better than yours, so.
That's true.
Fire. All right. Let's move to the next. Number 7. What phase increment will produce an output waveform of 440 Hz?
So you just solve for x over 16 times. Oh, how many bits are in?
Oh, 16 entries.
16 or 30.
Oh, bits? What do you mean by bits?
16 entries.
Yeah, 16 entries, right?
So x over 16 times 10 microns.
Okay, so I'll just give you the answer here for this one. This time, directly give you the key here. What's the number, what's the result?
14 increments. Or, well, I guess it's
Oh.
14.08.
No. This is microseconds, right? Wait. Yes, microseconds. So the result is 0.0704.
2 zeros, right?
I got one. Anyway, let's just assume this is right. Doesn't yeah, sure, calculate since you guys are turning it in, right?
Because last time we covered that it was 31.2.
Oh, that's something else. That's a different one.
Oh.
That's
Is that
that's a frequency resolution.
oh, okay.
That's something else.
Oh, okay.
That's the one you already turned in, right?
That was last. I was just.
That was last one. Yeah, that was last one. Yeah.
Okay.
44 over 625.
All right, let's assume this is right. Okay. Phase increment is this guy. Then we have to convert it to a certain format, 4.12. What does that mean? Fixed point, fractional numbers. Fractional numbers in the computer register. Okay? So like yeah, what's that?
It means 4 bits before the decimal place.
Yes.
12 bits after the decimal place.
Yeah. So basically what is this doing is you are telling the computer that what kind of format you are using. Okay? So you want to treat these bits as fractional numbers. Does that make sense? But there's actually no points in the register. These are just the memory cells. You know what I mean? The computer is treating that part, okay, that number of bits as a fractional number. That's how that works. So we know it's given, so you have to give that to the computer so that it knows it's working that way. But eventually it's just a 4 plus 12 number of bits. It's just like 16 binary numbers. All right, how that works. This is the number you want to represent it in this format for the binary number. So left shift by 12 bits first. Okay. Get all the numbers to the right, to the left side of the point. Even though you know this is not, it doesn't have 12 bits, but since it's the same number as what number you are converting to, so you are assuming there are 12 bits after the point. Assuming. It's okay, it's the same number, right? You assume. Okay? Then you left shift by 12 bits, which is equal to what? Times what?
2 to 12.
Okay? So this equals something, right? I'll let you guys, if you have a calculator. What is it?
288.358.
Yeah? Let's round it to something. Anyone else getting a number somewhere? Okay? So it's going to be something, right? Point something in decimal. You drop this bit, you drop this fractional number, round it to here, to this. Okay?
288.
Yeah?
Let's do that, but
Yeah? So what is that number in binary? This number converted to binary. Use 16 bits because we are having 16 bits here, 4 plus 12. And after that is done, shift it back to recover it. Then you're done. That's how to deal with this type of problems. Okay? There will be some problem like this in the final, okay? Make sure you know how to do it.
So you need to just left shift it.
And shift it back, yeah. Right shift it back. What's that? No? Okay, any questions? You shift it left, shift it to the right. Eventually it's not changing, right? Okay. Okay, I'll let you calculate it, turn it in to get the credits. Can we move to the next over here? What is that? What output waveform frequency will, oh, this is the easy one, okay? This one, how to do it. It's a very traditional frequency calculation problem. Remember, frequency out equals what? Phase increment divided by what? The sampling rate times the number of entries, right? Oh yeah, sorry. Phase increment of this produce. What output waveform frequency will phase increment of this produce? Number 8. What did I do? Oh, still assuming 10 microseconds and 16 entries. Okay.
771 hertz.
How much? Oh yeah. Assuming 10 microseconds and 16 entries. Okay, just one practice on this traditional problem. Okay, do that, calculate it. Any questions by far? Anything? No?
Did Colston do some of this stuff on his website with the 4.12 format?
Yes, he did. He used a dimensional analysis, but I think this is easier
Okay.
for me. But depending on your interest, what works for you the best. Okay?
Do you always throw away the decimal, or you just round it in when you do the times 10 to the 12, the left shift?
Since you only need 16 bits, right?
Mm-hmm.
I think either way, it's just a precision thing. You could also convert that decimal number, the fractional number here in the decimal, into a binary part as well.
Okay.
But definitely it won't be exactly like 0.25, 0.5 things, right? It could be something else. So eventually you have to round it to something. Okay? Any other questions? No? Next. Number 9. Okay. So it's asking, since frequency is given, sampling rate is given, number of entries is given as well. So you can calculate for what? The phase increment. It's asking you to convert that phase increment number to 3.5 format. Okay? So 20 kHz equals so what you got for this, let me know, okay? Equals what? So you can notice that over and over again we are using the same equation. It's a pretty simple kind of problem. So you are getting what? So you know that because these are all decimal numbers, so eventually this one will be a decimal number. So even though we don't know the number yet, but you should know that how do we convert it to this format, right? How? What's the first step? See? 5 digits. 5 digits. So what you want to do? Yeah, shift by what? 5. Shift by 5 to the left is the same as times 32. So times 32 first. Round it. Convert to binary. Then do this. Okay. Hopefully you already made some notes over here. Have you? We got 7 minutes. We have to finish the last one, so give you 1 more minute. So we have we'll take 6 minutes to finish the last one. Last one doesn't require any calculations, so it's actually easier. Let's see.
This right shifting divides by 2 raised to the f bar, so 2 is 4 divided by 4.
Remember, no matter how you change it, decimal binary is still the same number. So still the same number. Even though it doesn't make sense that you left shift a decimal number, right? But when we are doing the left shift, we are treating this guy as a binary number. So we are actually times 32 instead of really. Oh, did you shift the decimal number? Don't do that. Hmm?
Oh, you did 1.6 times 2 to the 5th?
Yeah, times 32. You're not times like 10,000, right? Yeah, 51, yeah. So we got 51, right? 51, then you shift it back, right? Okay, let's take a look at this one really quick. Interpolation. It happens to the sampling systems. So the problem, let me introduce the problem first. Okay. So a sine wave being sampled for every 4 points. So we're skipping 4 points and sample 1. Okay? So there's an issue that if the input is 7, how would you like to give the output from the system?
0 fill, or you can interpolate?
We can interpolate, yeah, interpolate. So it's called interpolation. So the way that works is use this equation. So we assume that the curve between 4 and 8 here is linear. So we use a slope to calculate the not given unknown x input over here. So 4, you have a number here. 8, you have a number here. But 7, you don't. And keep in mind, you have to be clear on that. 7 is the input. So to design a system, you need to know the input and output. Okay? So what's the input here? 7. It's whenever there's the input in between the ones we know, okay, you still want to give an decent output. So I have to give an estimate. Okay, so it's called interpolation. What you do is like this. F4, F7, FA. These are known because you know it's 7. So that's why you can assume that it's going to be F7, all right? But you don't know what that is. So F7 will be the output. 7 is the input. Is that clear? You design the system, you define, I have 4A, 12, but no 7, right? If the customer throw input as 4, I know the output. Throw 8, I know the output. 12, I know the output. But 7, I don't. So that's why we want to use interpolation here. And here is the equation to calculate it. Okay? And eventually you use, this one can be converted to this equation easily. So there's no magic on that. I'm not going to do that for you because there's no magic over there. So the problem is when the input is 7, how do you know that it's in between 4 and 8? Are you getting my point here? You don't. It's just the input. The computer system should be able to make a judgment that's in between 4 and 8. Then you are done. But however, you don't know that. Okay? That's the whole point of this program. Take a look. So when I'm talking, you want to make notes because you have to turn it in like in 2 or 3 minutes, okay? Let's see. These are the numbers you know, okay? And you want to shift that index to the right by 2. Why is that? You are skipping 4 points. So divide by 4. So you're getting the integer part of it. What that mean? What does that mean? Okay? F0, F4, FA, F12. They are being stored. They are being stored in a new array which has an index of 0, 1, 2, 3. After they are sampled, they are being stored in a new array, and the index is this. Okay? I know these were skipping 4 points. So if I have an input, for example, input 7, okay? How do I know which 2 points I should look at in between which 2 points? Divide by 4 and get an integer. What's the integer here? 1. So it's going to be after 1, before 2. Does that make sense? Okay? So that's why we have this. Shifted by 2 times, which is actually dividing by 4. So given the input 7, you divide by 4, you know that in the new array with the new index, it should be after 1 and before 2. Taking out the integer here. Now you know that you want to take out these 2 points and plug into where? To this equation. So now we know this because we know it's the first one is a 1, and we know it's the next one is 2, and now we still need to know this coefficient here. How do we get that coefficient?
Fraction.
As a fraction. So since we right shifted by 2, we get an integer. So if we don't shift it, the two digits will be the fraction part of it. Does that make sense? You shifted by 2 bits, you get an integer, right? So what has been shifted out? The fractional part. But that one has to be divided by 4 first. Because everything has been shifted to the right by 2 bits. So everything has been divided by 4. So that 2 parts divided by 4 will be the fractional part of it. So what is it? So 7 over 4 minus 1, which is the fractional part, right? So what is it? So what is this? 0.75. Okay? It's going to be these 2 bits and divided by 4 as well. So if you look at this, I know it's going fast. I'm sorry, we are running out of time. So I'm not going to give you taking too much points over here as long as you put some comments based on what our understanding here. So see this one. This minus this is giving us what?
The numerator of our equation.
Yes, this guy. Okay? Then come back. What is this one doing? X and this guy is taking out the 2 bits, the fractional part. See, the fractional part is over here times this guy is exactly what the equation does over here, all right? Anyway. All right, please turn it in, and we'll see you probably in the lab, okay?
Definitely not.
Well, also